Welcome back to week 3, and in this last video, video 5, we are going to talk about metamorphic rocks, how you identify them, and how you interpret the history of that metamorphic rock. So we're going to look at very similar stuff as we did in sedimentary and igneous rocks. We're going to look at the texture, and we're going to look at the mineral composition. The new thing we're going to add to this is to look at the parent rock, and this is what's going to help you. The mineral composition and the parent rock are what is going to help you to distinguish the history of that metamorphic rock. So texture, we've got grain size and arrangement, and one of the things we're going to look at for grain size, before I jump ahead here, is it coarse? Can you see it with the naked eye, or is it fine? Is it too fine for you to see with the naked eye? Those are the two main categories we're going to use for metamorphic rocks. Grain arrangement, is it foliated or non-foliated? We'll talk about that in the next slide, as you saw. And then, are the grains fused together? We'll talk about that too. So, foliation. Foliation is the alignment of platy minerals that are perpendicular to the direction of stress. So here I've got this diagram here where I have the yellow arrows squishing that rock, and then you can see the minerals are aligning themselves perpendicular at a right angle to that stress. And what we see in our rocks here, I've got the white line on each of these metamorphic rocks. It's showing you how those mineral grains are actually aligning themselves. So even in rocks that are too fine grained, such as these bottom two, so you can't actually see the mineral grains with the naked eye, you can still see the expression of that foliation in that rock, and it tends to break off into those flat layers. Sometimes the coarser ones you can actually see the minerals stacking up and aligning themselves, and here this one, the minerals are all aligning themselves as well. So foliation, alignment of minerals perpendicular to the direction of stress. What happens here is because you have the rock being squished so much, lots of pressure, what happens is any minerals that might be parallel to that direction of stress, they're not happy. They don't want to be squished that way, so that mineral ends up kind of recrystallizing very slowly from being parallel to the direction of stress, and eventually will recrystallize perpendicular to it. Very slow process. The rock never actually melts completely, but we have this just slow change that happens over time. Banding, what happens here is with intense amounts of pressure and heat, like minerals tend to clump together in these parallel bands. So we start out with foliation, and then if we keep that pressure on and that heat on, the minerals will eventually start to separate out into these different chunks or layers. And here you can see kind of these color bands present in the top rocks. And you can see here how they've kind of recrystallized into the different color bands. And when a high stress is applied, so we keep that stress on, we can end up with very wavy layers in the rock, like you can see here. And then fused grains, basically when you have a rock that has all the same type of mineral composition, if we increase the heat and pressure on that rock, the grain boundaries tend to disappear. So similar composition minerals combine together or fuse into one another. So we can't actually see those grain boundaries anymore. And here it kind of has a sugary-like look to it. It looks kind of like maple candy, if you've ever had that. I love the food analogy. So you can't see the actual grain boundaries anymore. So mineral composition, well, minerals that we're going to see, calcite, it's going to react to acid. Quartz is going to be harder than glass, just straight all quartz, it's not going to react to acid. We can see quartz, feldspars, micas, and amphiboles all in the same rock. Here we can see the quartz and feldspar in the lighter bands, and then the mica and amphibole in the darker bands. We can have straight amphibole in a rock. Amphibole, hornblende, pyroxene, same kind of stuff. And then we can also get just straight mica in a rock, muscovite and biotite, or we can add garnet into that rock too. And garnet is a sign that you have metamorphism. Garnet only forms under metamorphic conditions. So garnet tends to be these kind of round, spherical, purplish, reddish colored blobs in your metamorphic rock. So that's your chemical composition, your mineral composition present in these rocks. So when you're asked to tell me the major minerals, that's what I want. If you can't see it, you can't tell, you're going to put Na. So the next part is the parent rock, and this is going to help you tell what's happened to that rock in the past. Certain minerals are going to be signs of specific temperatures and pressures. There's a great diagram in your textbook to help you out with that. I'll try to bring copies of that to class, so if you don't bring your textbook, we'll have one here. So you're going to have specific conditions that different minerals are going to form under, specific temperatures and pressures, but also you can tell what that rock used to be. Sometimes it's a little difficult. You can maybe make an estimate or a guess in some cases, but in things like quartzite and marble, both of these, quartzite and marble, have uniform compositions. Quartzite's made of quartz, marble is made of calcite, and both of these are coming straight from their parent rock. So quartzite is going to, you can trace that back to a quartz sandstone. Totally pure quartz in the parent rock, totally pure quartz in the metamorphic rock. So sometimes you'll have very similar mineralogy present. The grain size is only going to increase from parent to metamorphic because we have minerals that might be combining together or recrystallizing to form new ones. We don't have any complete melting. No complete melting happens at all with metamorphic rocks. Unlike igneous rocks, if the rock melts completely, then you're going to get an igneous rock that forms. So grain size is only going to increase. So, for instance, this quartzite, we see it kind of has a uniform grain size here, fused grains. It probably came from a sandstone, not something like a conglomerate, because a conglomerate not only does it have really big particles, but it has lots of different types of particles too. So the other thing to think about is, well, how do we get these ones that are banded or foliated? Well, what happens is we start with a shale. So we start with a rock that has just purely clay minerals. And as we slowly increase the heat and the pressure on that shale, those clay minerals start to rearrange themselves. We start to break some bonds, form new ones, and we get slate. So basically slate is those clay minerals are getting compacted together. It's very dense. Slate and shale are really hard to tell the difference between these two. I'm not going to ask you to do that on a test because that would just be mean. Even I have a hard time sometimes because they look so similar to one another. Usually slate's going to be a little bit shinier and it's going to be more dense. If we keep increasing the heat and pressure, we get phyllite. We start to get things like chlorite and graphite starting to form if there's any carbon present in that original shale. We start to really see more of that foliation. More of those grains are aligning themselves. We increase the heat and pressure even more, and we start to actually see minerals forming. So we start to get what's called a schist. And a schist is where we have actual mineral grains that you can see with the naked eye, and they're foliated. So your schists can have micas present, garnet, chlorite, talc. You can have some quartz present and amphibole. So the schist is a smaller, schist can be broken up into different mineral compositions. So in lab, if you see a schist that has mica in it and it has some garnet in it, whichever is the most abundant goes right next to the schist name. So if it has a ton of mica in it, a couple bits of garnet, you're going to name it a garnet mica schist. And then the next step, if we increase the heat and pressure even more, we get those bands starting to form, and we end up with what's called a gneiss. And a rock that has banding is called a gneiss. Hey, that rock has nice banding. It's a good way to remember it. That's how I remembered it when I was in school. So to tell the history of a rock, sometimes you have to think about this process, this transition of metamorphic grade. So they start at the top, low grade, low temperature, low pressure, high grade at the bottom, high temperature, high pressure. So you can look at it that way. You can look at the parent rock, what was that rock before it was altered, and then also look at the minerals present to get, okay, was this high grade, was this low grade, do I think that there was a plate boundary here, things like that. And make sure you review your textbook on some of the really great metamorphic features and diagrams. So I'll sign off and see you in lab.